getting toward the end of topics here. So we're much of the way through nuclear weapons. Just to sort of rehash a little bit what the story is, it's that the very largest of the nuclei, things like uranium, plutonium, these nuclei have so many protons in them. First off, they need a lot of neutrons in the nucleus to dilute the protons so that they don't simply fly apart immediately. So these are nuclei that are 92 protons for uranium, 94 for plutonium, well over 100 neutrons spreading out the protons. They have a lot of energy stored in their electrostatic repulsion. They're held together by the nuclear force, but kind of tenuously. And many of these giant nuclei, certainly everything from uranium up, they're all naturally radioactive. There are some elements earlier on that are radioactive in every isotope. There are no existing stable isotopes, for example, of francium. So a few of those nuclei getting close to uranium just aren't around, or not in any quantity. People discovered that not only are some of these nuclei, these giant nuclei, radioactive, but they decay in a way that isn't just the emission of sort of one particle coming out of them. A lot of radioactivity is just the ejection of approximately one particle, or a pair or triplet of particles, but a very small thing comes flying out. Uranium-235 is capable of another kind of shattering, and that is the breaking into large chunks, what's called fission. And what about it? It happens to some extent spontaneously, but it certainly happens if you hit the uranium-235 nucleus with a projectile that actually that rings its bell. A neutron can sneak up on it and really smack it. In fact, it gets sucked in, so even a very slow-moving neutron will shatter it. It doesn't have to hit hard because it's sucked in by the nuclear force and effectively hits hard anyway. So once people figure out that there are nuclei that do this, the idea of making a nuclear weapon was pretty straightforward. You got to get a whole bunch of these nuclei together. You have to have an initial nucleus, neutron, to break the first nucleus, and then you have to have those nuclei, the fissionable ones, close enough together that they efficiently use each neutron that's created in a decay produces at least one subsequent decay. And so you get this building process. So the chain reactions can build up, they can build down. If with each generation of shattering, you have fewer and fewer neutrons, then the whole thing builds down. And this kind of thing is important. We'll come back to it in looking at nuclear reactors shortly. So you can have the reaction build up, more and more and more neutrons, or build down. In principle, you could run and break even. It's hard to maintain that because it's very fine. There's a sort of a fine-tuning issue. And with the nuclear weapons, they deliberately go for a building up. Generation after generation gets more and more neutrons, and they try to make those generations grow as fast as possible. So the first generation might have a single neutron. The second generation might have 3 neutrons flying out. Next generation, 10. Next generation, 30. Next generation, 100. Next generation, 300. It's growing rapidly, and I think it's an exponential growth. All right, and once you have that sort of system available, the only real trick left is getting the materials together fast enough so that you don't sort of get the reaction started before you've actually built the critical mass of material, so that a bomb can fizzle if in the act of bringing it together the chain reaction begins to appear there, and it heats up, not to the sun type temperatures, but to thousands of degrees, and it heats up and things expand, and things turn into gas. And it could all fly apart before much has happened. It just got hot and blew apart almost like a conventional bomb. And those are the famous dirty bombs you hear people talk about, where it doesn't really make a huge explosion, but it sends all kinds of crud, radioactive crud all over the place. John?
When you're bringing the two atoms together,
Yep.
and form like an unstable nucleus, how do they prevent it from like reacting all by itself? Because they naturally don't want to go together anyway. So would it cause a reaction if you try to bring them together just initially, or just like slow down?
I'm not quite sure I know the question, whether you're thinking of bringing together huge blocks of material or individual nuclei.
Let's say individual nuclei.
When you bring together individual, it's very hard to bring two nuclei together because any nucleus is going to have positive charge on it. So two nuclei hate each other; they push apart. But you can bring a neutron in, which is stealth attack, and that's the usual trigger for this kind of shattering of nuclei, is bringing in a neutral object. Is it okay? So I told you, I'm going to flip back just to remind you that the two ways in which people managed to make nuclear weapons, era of World War II, was this one where they took a sphere of uranium-235 and completed it with a cannon firing a cylinder into the center of a sphere that was missing a cylinder. Once they had assembled that, they had the so-called critical mass, which again, it's a little bit of a misnomer. It's not literally the mass that matters. It is the mass plus how it's organized, what's around it. For example, if you put neutron reflecting stuff outside the portion of uranium-235, it can reflect the neutrons back in, so you use them more efficiently. All kinds of little details matter. And so in this case, before that cylinder went into the imperfect sphere, it was below critical mass, meaning that it could not sustain a growing chain reaction. It could have, one neutron could cause a fission, which might cause another fission, or it might not, which might cause another fission or might not, and it would piddle away to nothing. So basically, any little chain reactions that showed up were dying and decaying ones that didn't actually go anywhere. Once they'd put the whole sphere together, which took some thousandth of a second or something like that, because the cannon moved this thing into the center of the sphere. Once they assembled the critical mass, now each neutron would tend to produce more than one neutron, would tend to produce even more and more and more, and you get a growing, or in fact an explosive chain reaction where it's getting larger fast, and that's how that went. The people who developed that bomb were convinced it would work. They'd sort of tested all the issues so well. They knew it would work. They didn't want to test fire it, because obtaining that much uranium-235 was just a crazy hard work. It was, I don't know how many thousands or more people were involved, and years and years of work assembling that 60 kilograms of uranium-235. And the reason for the difficulty is, first off, uranium-235 is a rare nucleus in a much more abundant uranium-238. And the numbering scheme, just make sure you understand the numbering scheme. That 235 up there is a reference to its total number of nucleons, what's called the atomic weight. And that distinguishes it from uranium-238, which has 3 more neutrons, a longer life, and is far more abundant in nature. Because of its longer life, the uranium-235 falls apart more frequently, and therefore it's dwindled away since the Earth was formed. Separating it, the only way they could separate it is by mass. And so this is, when you hear talk about nuclear proliferation issues, centrifuges and stuff, Separating 235 from 238 is hard. People have done it with mass spectrometers, with centrifuges. In fact, the University of Virginia was involved in isotope separation centrifuge projects up on Observatory Hill. This building is named after Jesse Beams, who was a centrifuge person. That was his expertise. Very hard to separate, because chemically you can't tell 238 from 235. They're just the same chemically. Is that okay? The other nuclear weapon from World War II was the plutonium weapon. In this case, they synthesized plutonium. How do you make plutonium? You run a nuclear reactor, which we'll talk about shortly, and the 238 gradually transforms, uranium-238 gradually transforms into plutonium-239 in the presence of a lot of neutrons. And so during the war, they were running nuclear reactors that were powered by uranium-235, but they used some of the neutrons coming off those nuclear reactors to irradiate uranium-238. And when uranium-238 gets hit by a fast-moving neutron, the kind of neutron that comes flying off of an exploding uranium-235 nucleus. So when that uranium-238 gets hit by the neutron hard, it captures the neutron, it grabs it, and now it has one too many neutrons. And I told you, neutrons get lonely, they fall apart, and the first thing that neutron does is it falls apart into a proton, an electron, and this antineutrino. Off goes that little thing, the little antineutrino. The electron goes off and wanders around the wide world, and the proton becomes part of this, what was briefly uranium-239 suddenly becomes neptunium-239. And neptunium-239 is also unstable. It's got one too many neutrons at least, and another of its neutrons falls apart. Out goes the electron and antineutrino, and the proton's left behind, and it evolves from neptunium-239 to plutonium-239. And plutonium-239, although radioactive, has a life of something like 25,000 years, a half-life. So half of it goes away every 25,000 years. And that was the basis for the two of the nuclear weapons used in World War II, and this is the one we're all worried about. This is what's at the core of these things that North Korea has been blowing up. Is plutonium-239 created in nuclear reactors by irradiating uranium-238. All right? Because plutonium is so radioactive, you can't do the cannon fills in the center of a sphere trick. They realized this early on. The assembly is too slow, and what will happen is the slug, the cylindrical slug of plutonium trying to fill in the sphere, the chain reaction will start immediately when it's possible, and it will happen before the slug really gets into the center of the cylinder. The chain reaction will already kick into gear. It will grow very fast, but not the way they want for an explosion. It'll get really hot really fast, and the whole thing will come apart before it really had a chance to shatter all its nuclei. So you get a dirty bomb. You'll get a modest explosion that sprays a lot of radioactive stuff everywhere. So they knew they could not assemble it mechanically. They had to crush a sphere of plutonium to abnormal density, and they can do this with high explosives. It surprises me you can do this, but apparently you can do this. You can get an inward, a lot of momentum inward to push the material so that it bounces off itself, basically crushes inward, and the density will go up to several times normal density briefly before it pops back apart. And during that high density moment, neutrons suddenly are able to hit things so reliably because all the nuclei are packed close together, it's hard to miss. And you get an explosive chain reaction. All happens in a fraction of a microsecond. All right? So those are, they were not confident, they were confident, but not confident enough in this plutonium idea to not test it. Plutonium was easier to produce because it's chemically unique, and they could strip it off from everything else with chemical means. This is why countries that have sort of research reactors that are capable of irradiating uranium-238 with neutrons can produce plutonium. They can get the plutonium out and they can make bombs out of it. Much harder to obtain a lot of uranium-238, 235, because it's so difficult to separate. Anyhow, they tested this at that Trinity site in Alamogordo, New Mexico, and then they dropped it on another one on Nagasaki. All right, so those are the stories of, hopefully those will be the only such weapons ever used in outside of tests. Fallout. So you've seen where the explosion comes from. It's from taking these giant nuclei, smacking them so they come apart, and off go all the fragments. Well, the giant nuclei, in order to be even temporarily to have any life at all, they had to have a lot of neutrons in them. More neutrons, pound for pound, than all the smaller elements. So the smaller elements, like the ones we're made of, the nuclei have their certain number of protons, a dozen or so, and they have some neutrons in the nucleus to dilute the protons, but there are not so many protons to dilute it. It's not so important. The dilution isn't such a big issue anymore down for the little nuclei because they don't have that many positive charges repelling each other. So things like ordinary iodine and ordinary cesium and ordinary strontium, they have a certain number of neutrons and maybe some flexibility, but a modest number for the size of the nucleus. If you look at the fragments produced when a chain reaction occurs, and I can flip back to that one. I'll play games with my slides. There. If you look at all the shrapnel that comes flying off, here's a zirconium nucleus, tellurium. I don't even know what 141 is. Strontium. The labels are screwed up here. But I think labels have gotten out of whack here. Lanthanum, this. That's really messed up. Oh well. The pieces that come off tend to have too many neutrons. Some of the neutrons came off all by themselves, but some certain number of them remained attached to the sort of the nuclei that flew out. There tend to be too rich in neutrons. Lonely neutron problem. The neutrons tend to break apart, and you end up, when the explosion's over and all the dust settles, I mean, just for starters, there's some unexploded giant nuclei, whether they're plutonium or uranium, and those are not great. They have relatively long half-lives, uranium in particular. I mean, plutonium you don't want to be around. It's nasty, hazardous stuff. But at least your body has no important use for it. So it's not like if it comes along, your body goes, ooh, I need that. That's not true of iodine, and which is it? Iodine 131. Normal iodine, I think, is 127. It's got fewer neutrons. Iodine 131 is easily made by nuclear explosions, and it has by bad luck, it has a half-life of 8 days. If its half-life were 100 million years, it wouldn't be a big deal. Because yeah, your body would incorporate it into your body. You use iodine in your chemistry, chemistries of life. If it had a very long half-life, the chances that any given nucleus would explode during your lifetime is small, and it wouldn't be a big deal. If it had a very, very short half-life, which would make it wickedly radioactive, yeah, for a day it would be dangerous, but then it would be all gone. Just it burns up in minutes. It's these things that have half-lives that are sort of in the days to low number of years that are nasty, because they're radioactive enough to be dangerous, and they're long-lived enough for them to get into you. And so the ones that they particularly are worried about in the nuclear weapon stuff, and also in the spent fuel from nuclear reactors, I've listed 3 of them: iodine-131, cesium-137, and strontium-90. These are both radioactive imitations of conventional elements that we use in our bodies. And your body will go, oh, it's an iodine one, it's an iodine atom. That's good. We need iodine. Build it into something. And over an 8-day period, there's a 50-50 chance of whatever it was built into, whatever molecule it was built into, to have this terrible explosion, ripping apart that molecule in a lot of the vicinity. So you don't really want to be exposed to these. You want to get them out of your body as fast as you can and let them explode somewhere else, not inside you. Okay? So they're all these overly neutron-rich isotopes of ordinary elements. That's fallout. Any questions about the stuff that comes out of nuclear weapons? Explosions. Things you're curious about. What I'll add to this, that's not in my notes, is the other half of nuclear weapons, which is thermonuclear weapons, or hydrogen bomb. I told you that the giant nuclei have a lot of energy stored in electrostatic potential energy, and when you assemble them, the act of pushing them together required a tremendous amount of work. They then grabbed onto each other and did a little bit of work on you at the end, and then they're stable for a while, or maybe forever, but maybe not. But the point is that the energy that matters in that for the big molecules, big nuclei, is electrostatic. For little nuclei, that strong, the nuclear force that sucks nucleons together is more important, dominates, is sort of the biggest thing around compared to the electrostatic repulsion of the protons. So if you bring together little tiny nuclei, an act which requires some pushing and work, a little work, because you're pushing together positively charged things. If you push them together, it doesn't take a huge amount of work on the grand scheme of things. Till they're about to touch, at the point of touching, then the nuclear force pulls in on them and does a lot of work on you. So the point being then, you can do a modest amount of work to get them close to each other, and then they do a lot of work on you as they finally pull together at the end. This is a process called fusion. It's what powers the sun, for example. The sun turns out it takes 4 hydrogen nuclei, 4 protons, and through a very complicated process, it assembles those into helium-4, which has 4 nucleons in it. Turns out 2 of them are protons and 2 of them are neutrons. So it's had to transform 2 of the protons that it started with 4 protons. It has to turn 2 of them into neutrons, which it can do. It's in a certain situation, but it's a very slow process, which is why the sun has been cooking away for billions of years. The act of finally pulling it together and building that helium nucleus out of 4 littler nuclei released a lot of energy. And the energy finally was contributed by the nuclear force pulling everything together at the end. So You can release energy assembling little nuclei. You can release energy by disassembling big nuclei. There has to be a middle ground. There has to be a sort of some size at which you can't get energy in either way, and that's around iron. The iron 56 nucleus is the most stable there is. That is, anything smaller than iron 56 is building toward iron 56. Anything bigger than iron 56 is breaking up, trying to get to iron 56. It's like the ultimate perfection. And so the nuclear weapons, the original ones, the fission bombs, were breaking apart big nuclei, sort of heading towards iron 56 from above. The subsequent fusion bombs were doing the opposite. They're building bigger nuclei from below, trying to get to iron 56. I mean, as the ultimate goal. They never get there, but that's okay. So how do you make a fusion bomb? In the sun's got infinite patience. It can sit there, and it's under the nuclei are under tremendous pressure, very hot, and they're bouncing off each other, and occasionally you get four of them to come together just right and turn it into helium, and energy's released. So you can wait all day. For a nuclear weapon, you can't. And so the way they work, those fusion bombs work is they start with nuclei where it takes only a pair to hit each other and stick to release a lot of energy. You don't want to have four things come together. That's so unlikely. You need long patience. So they use simple nuclei where two of them hitting and sticking is all it takes, and they heat the bejeebers out of them. How do they, really hot. How do you make them really hot? Why do you need them really hot? First, it's so that they hit each other. If you have two nuclei that aren't in an environment that's not very hot, first off, they're going to be parts of atoms, and they're going to be wandering around each other and bouncing off each other like gases. So you want them so hot they don't even notice they have electrons anymore. And you want them so they're just nuclei. Forget the electrons. And the nuclei repel each other. So you need to have them going so fast and so hard that they just burrow right through that repulsion and hit anyway. So that's why you need tremendous temperatures. Not like blast furnace temperatures. You need like hundreds of millions of degrees. Almost billions of degrees. So that they're going so fast and so hard that the nuclei just burrow right through any repulsion and hit each other. And the only way people know of to produce temperatures like that on any large scale is with another nuclear weapon. So all of the fusion weapons start with a fission bomb. So they start with a uranium or plutonium bomb. That gives them the high temperature necessary to heat materials hot enough to initiate fusion, where the small nuclei stick to each other. All right? And the projectiles of choice, again, ordinary hydrogen won't do it because the nuclei is just a proton, and you're not going to get a whole bunch of protons to assemble themselves into bigger nuclei in short order. You need more complicated nuclei. And the nuclei of choice for that are the heavier isotopes of hydrogen. The most ordinary hydrogen, which you're built, has only a proton as its nucleus. It's the simplest, lightest nucleus there is. But there is a small fraction of hydrogen that has a different nucleus. The nucleus has one neutron in it. It's a proton and a neutron. And that's the nucleus of an atom known as deuterium, the heavy isotope, the heavy naturally occurring isotope of hydrogen. So you got a little deuterium in you too. You don't want a lot of it. It messes up your chemistry. People have done these experiments where they've concentrated what's called heavy water or heavy hydrogen. They'll concentrate it and they'll see how it affects life, and it messes up animals. You don't want to do it. So it's chemically the same as hydrogen, except that it's got about twice the mass per atom, And that's enough of a change that even the chemistry starts to be a little different. So you don't want to have it around. You understand then what deuterium is? Is that okay with that? Questions about? And there's also a third isotope of hydrogen known as tritium, which has 2 neutrons and a proton. And it is naturally radioactive with a half-life of, I believe, 17 years. So it's got to be synthesized. It doesn't occur in nature, but it can be made. And it is made, and it is part of nuclear weapons. And this is one of the reasons why the nuclear weapons stockpile has to be regularly babysat. It's because it's got a lot of it's got tritium in it, and the tritium gradually decays away, and you have to replace it with more tritium made at nuclear reactors. So anyway, deuterium and tritium, when you heat those babies up and smash them into each other, they fuse. And you don't need these rare multi-way collisions that the sun uses. The other other convenient source of small nuclei for fusion is, oddly enough, lithium-6, one of the 2 lithium naturally occurring, the rarer, fortunately, lithium isotopes. And this is a concern at present because North Korea, some countries was selling a lot of lithium-6. And lithium-6, when it gets hit with neutrons, breaks, I believe, into tritium and deuterium, which then can fused into helium. It's some messy process that I used to remember and then promptly forgot. In any case, a big block of lithium deuteride or something like that, based on lithium-6, you could basically make a solid material that if you expose it to the blast from a fission bomb will undergo thermonuclear being hot nuclear process. It'll undergo fusion, and it will evolve into some other nuclei and release outrageous amounts of energy. So people are concerned about the heavy hydrogen isotopes floating around on the world economy or whatever, lithium-6 floating around. They're all problems. A big problem with thermonuclear weapons. Again, the word thermonuclear is a reference to you use the temperature of a fission bomb to ignite a fusion bomb. And the problem with fusion bombs, is the sky is the limit in terms of how big they get. Fission bombs are limited in size because you can't, once you've assembled a critical mass, it goes poof, kablooey. You can't sort of bring in more and more material and make the bomb bigger and bigger because you'll hit critical mass. It will explode before you've assembled more stuff. So the fission bombs all have a sort of a ceiling of how big they get, how big a kablooey you can make. The fusion bombs, you can go as big as you like, and during the Cold War, the U.S. and particularly Russia went just hog wild and made these unbelievable, like 100 megaton bombs and stuff. Because you use a fission starter, and then you just can have like a room full of these hydrogen or hydrogen-related nuclei, blow them all up. And so that's why the hydrogen bombs potentially are just fantastically large. From what people have seen, there are photographs, for example, that have come out of North Korea showing a picture of what is supposed to be a bomb. It probably is, I guess. And so the experts are all analyzing whatever. And it's a plutonium bomb. It's these high explosive lenses that are there to crush a plutonium core. And so that says how big the bang can be. If that evolves into the trigger for a hydrogen bomb, well, then the bang gets a whole lot bigger. And time will tell. All right, I think I've said my piece about nuclear weapons, sort of. You got any questions about this stuff? All right. So, that's the sad side of nuclear reactions. The less sad side, the side that's more promising, although it's fraught with its own perils, is nuclear reactors or nuclear power generation. So the next story then is how you use nuclear reactions to make power in a controlled way. You obviously don't want it going kablooey. So this question then, if you design a nuclear reactor with a chain reaction occurring in its core, suddenly loses water that cools that core, the chain reaction will do what? And this is foreshadowing the role of water in a nuclear reactor that's designed properly. If you suddenly lose the water, what do you think is going to happen? That you'll get the chain reaction will grow explosively and you'll blow the whole thing up? How many think A? How many think that nothing much will happen? Unchanged. B. How many think that it will stop spontaneously? The nuclear reaction will actually decay away. Okay. The majority of you are going for A, I suppose. 1 or 2 for C. Oddly enough, it is C. So in a properly designed nuclear reactor, and properly is the salient word there, the water is serving a role that if you lose it, you actually squelch the chain reaction. That has not always been the case, and it's, for example, Chernobyl. It was not the case at Chernobyl, and that's a sad thing. All right, so nuclear reactors provide a lot of energy, consume nuclear fuel, and all that kind of stuff. So the issue is sort of how do they work, and how can they use natural uranium? So here's the story. In fact, what distinguishes them, the normal nuclear reactor, from the fission bombs that seem to be the same thing? All right. Well, the story begins with those 2 uranium nuclei, 2 isotopes, 235 and 238. As I've said before, 235. It's the more radioactive of the bunch. It has a half-life that is under 1 billion years, and so it's a rare fraction of natural uranium. It's currently about 0.7%. It's fissionable, meaning that if you hit it with neutrons, it can shatter into just fragments. What about its bigger brother, uranium-238? It's still radioactive. It still throws out stuff. It's fissioning. It can fission, but rarer. It doesn't do as many of those breaking into similar-sized chunks. More often, instead, it throws out single particles, and its favorite single particle is what's known as an alpha particle, which is just a helium nucleus. It's just 2 protons, 2 neutrons, the nucleus of the familiar atom helium. And you wonder, where did the helium that you've played with all your life? Where do you think that helium came from? It came from natural gas wells, primarily in the United States. Helium exists in the air, the atmosphere, but it's so rare in the atmosphere that it's not commercially viable to extract it from the air. The helium that you all play with comes from natural gas wells, where it's mixed in to some extent, particularly in the United States, with methane, famous natural gas. And so where did that helium come from? Why is it down there with the natural gas? It was created by the Earth's natural radioactivity, the long, slow decay of things like uranium deep in the rocks that shot off particles. And the particles, the favorite particle to shoot off is this wonderfully stable nucleus, the nucleus of helium. So all the helium in your balloon, it came from radioactive decays somewhere eons ago. All right, so uranium-238, that's its favorite decay route, is to kick off a helium nucleus. And it's not fissionable, meaning you can't hit it with neutrons and shatter it. It laughs at you when you hit it with a neutron. It just catches the neutron and then it undergoes this gradual evolution into plutonium. So it's not suitable for nuclear explosions or even nuclear reactors directly. It doesn't, you can't crack it. Okay, so in natural uranium then, most of the nuclei are the wrong thing, uranium-238. There are a few 235s. And if you try to create a chain reaction in natural uranium, you run into trouble. The uranium-235s can fission. Actually, they fission, they can throw off neutrons. And one of those neutrons can be jetting along through the uranium, and if it hits a uranium-235 nucleus, it can shatter that one and cause starting to try to build a chain reaction. But it's much more likely to hit a uranium-238 nucleus and get captured and be out of the picture for the foreseeable future. So natural uranium is terrible for chain reactions all by itself. You can assemble, is this true? As much as you like. You won't get a chain reaction. Because, yeah, it's got lots of radioactive nuclei all together, and you can fill the room with it, but it's got these uranium-238s everywhere that tend to grab on to fast-moving neutrons, the very kind of neutrons that are part of the classic chain reaction in uranium-235. So the bomb chain reactions all involve neutrons whizzing around, smashing and shattering uranium-235 nuclei. And if you bring in and dilute the uranium-235 nuclei with their bigger brother 238, you're putting in neutron-absorbing stuff. Those 238s grab fast-moving neutrons and take them out of the story. So you can't make a chain reaction with only your naturally occurring uranium. Questions about that idea? Man, so what are you going to do? Does that mean you always have to get rid of the 238, or you'll never get a chain reaction going? Oddly enough, the answer is no, you can't. There's a trick. The trick is thermal neutrons, which is, what thermal neutrons? Thermal means neutrons that move with the velocity characteristics of room temperature. Meaning, so the neutrons that come flying out of a exploding uranium-235 nucleus are traveling really fast. They're crazy speeds. If you can slow those neutrons down so they're traveling the way gas particles travel in this room, they're moving, the gas molecules are moving pretty fast. They're moving 500 meters per second on average. But that's ordinary speeds for gas at this temperature. That's thermal speeds. If you can get the neutrons to move at thermal speeds, 500 meters, 1,000 meters per second, that kind of stuff, something changes. Those neutrons can still fission uranium-235. If they encounter uranium-235, it grabs them and bursts apart. What those neutrons no longer do is get caught by uranium-238 nuclei. Oddly enough, the uranium-238 nucleus doesn't care about slow-moving neutrons. It ignores them. It just lets them go by. It's boring. And so if you can slow down the neutrons that are created by the fissions of uranium-235, you can make uranium-238 as though it didn't exist. And so you can create a block of material that is effectively only uranium-235. It's diluted out because there are secretly uranium-238 nuclei present, but they're not doing anything. They're just ignoring everything. And that's how you make a thermal neutron. It's called a thermal fission nuclear reactor. You allow the uranium-235 nuclei to fission. You, as quickly as possible, slow down the fission neutrons to ordinary speeds before they have a chance to be gobbled up by uranium-238s. And you let those slow-moving neutrons wander around and crack additional uranium-235 nuclei. So all the nuclear, well, not, I should say, most of the nuclear reactors in this world, hundreds of them, are thermal fission nuclear reactors. They use as fuel approximately natural uranium. It may not be truly natural. It may be slightly enriched in uranium-235 for reasons we'll talk about. But the fact that it's got lots of uranium-238 doesn't squelch the chain reaction because those reactors all slow down the neutrons as quickly as they possibly can to stop uranium-235 from interfering with them. All right? And the way in which that's done, the slowing process, is to let the neutrons hit things that don't absorb them, but simply carry off their momentum and energy. It's like bumper cars. The neutrons come flying out of an exploding uranium-235 nucleus at tremendous speeds, but if they bump into, for example, a hydrogen nucleus, a deuterium nucleus is even better. That is the heavy hydrogen. Carbon. I think oxygen, I'm not so sure about it. Carbon's for sure. Those are probably the best ones, certainly the ones that come to mind. The neutron hits those, and it's like, you remember the bumper car, this thing? If you have two equal mass ones, like a deuteron is really good. That is the nucleus of heavy hydrogen. It's got a proton and a neutron. When this flying neutron hits that, first off, there's zero absorption of that neutron, never ever absorbed. And the masses are similar enough. The deuteron's twice the mass of the neutron, but they're similar enough that the neutron almost can come to a dead stop, and the little deuteron goes flying off, but it's okay. Hitting carbon isn't quite as good because carbon's a big thing, and the neutron hits it, and it tends to bounce back. It's like a bug hitting a windshield. Well, a bouncy bug. Anyhow, the point is, so the thermal fission nuclear reactors have a material in them called a moderator, the job of which is to slow down the neutrons. And the moderators that are used are water, for example, heavy water even better. Water, it's the nuclei in water that matter. So if it's a hydrogen and an oxygen and a hydrogen, hitting those, I think the oxygen is just not part of the story. The neutron doesn't hit the oxygen very often, but it hits the protons pretty regularly. If you have water that's heavy, that has, instead of normal hydrogen, each nucleus in the water of the hydrogen is a deuteron, a proton and a neutron. That's an even better moderator. Carbon is another moderator. And a lot of the disasters that have occurred, the nuclear reactor disasters, wind scale, which you don't know about, don't remember. Chernobyl, you certainly have. If you don't remember it maybe, but you know of it. That had carbon in it. Both of those had carbon in them as moderators, slowing down neutrons. And carbon burns and does all. You can get into real trouble with carbon as a moderator. So the Chernobyl disaster is more complicated than that, but the wind scale was very simple. Basically, the carbon caught fire. Anyhow, the point of the moderator: slow the neutrons down. Once you slow the neutrons down, you can run the reactor as though there were just no uranium-238 present. You need a bigger volume of uranium because to reach critical mass, you need more opportunity for a neutron to wend its way through this void that is uranium-238 and hit a 235. So the reactors become bigger. It's not suitable, for example, for use on a spacecraft. Too big. But you can get by with either natural uranium or almost natural uranium and still have a nuclear reaction and a chain reaction. And so the story next that I'll deal with on Monday is, okay, so you can make a chain reaction. How do you control it? Our only experience so far with chain reactions is once you get them so that the generations increase, get stronger with each generation, you get an explosion. Obviously, you don't want to have that happen in a nuclear reactor. And so there's some tricks there to also keeping those reactions under control so you don't blow things up. All right, have a good weekend and see you on Monday.